All right, everybody, here we are in the auxiliary classroom, aka my basement. Here we go. I got the treadmill out there, very important. I apologize for the mix-up for today. The entire building of Corbett and several buildings around campus had no Wi-Fi, so the ability for me to stream and get this information out to everybody obviously was not there. So we're making do. Got home, got my Wi-Fi up and running at the house, and got my iPad all synced up now. So I think we should be able to create basically the same thing. But I do apologize because I'm going to miss out on those real-time questions. But if you have questions, make sure to get in touch with me today because our exam is tomorrow. So get those questions to me today, and I will do my best to get those answers back to you. Okay, so what are we going to do? First off, a little housekeeping with the homework and the quiz being due last night. Though we had several people who I think those assignments kind of came up on them very quickly and may have missed those. So you have gotten your one freebie of an extension on that without any information or without any contact. Like I said before, I want to make sure that you guys know that extensions are going to be part of this summer semester. Things are very different right now than they have been in past semesters. I'm not going to be a crazy stickler. That does not mean you can just go about willy-nilly and then, the last 2 or 3 days of class do all your assignments without contacting me and expect full credit. What that does mean, if you understand that you're going to have some time constraints coming up, get in touch with me beforehand and we will make accommodations between the two of us that make the most sense for whatever you're dealing with. Or you realize immediately after the fact, the next morning, oh my gosh, I missed an assignment, get in touch with me right away. Don't wait till the end of the semester for some of those assignments to be due. And that brings me to one other big point. Got a lot going on in the world right now. I'm sure that unless you're living under a rock, you've seen everything that's been going on. The protests for George Floyd. We have coronavirus. With that being said, I want to make sure that you guys understand that the University of Wyoming has a lot of resources to help you on many of these fronts. Dealing with some of these situations is going to be, psychologically challenging. I know that me and my family are going through a lot, having a lot of kind of dinner table conversations about it. Fortunately, we have that support network here. And I know with people not being on campus, you might not have that same thing. With that being said, the University of Wyoming has a lot of resources, and I want to make sure that everybody knows about those and can access those if you need them. Or even if you think, I just want to talk to somebody about what's going on. Make sure to reach out to me because I can connect you with those sorts of resources and make sure that you're taking the actions that you need to make sure that you're healthy and move forward with this semester so that we can get you graduated, get you onto a job. That's what we're here for. Yes, this content is important, but making sure that you're well-rounded as a student and you're healthy and you're part of our University of Wyoming community is more important than that. So please reach out to me if you have any questions or comments about that, and we can make sure that that gets handled. Homework number 1. Quiz number 1 in the books. Hopefully you guys will start to understand about how I ask questions. Some of those quiz questions are a little hard. They're based on the textbook, so make sure you have that textbook going. If you have questions about why you may have gotten a question right or wrong, please get in touch as well. Okay, let's do a quick little review, and then we'll move on. Letter A here, describe the orientation of myosin and actin within the muscle fiber. Remember, muscle fiber is that smallest down kind of subunit within that muscle belly. Remember, we moved kind of down the order of operations there. But if we wanted to kind of develop what this looks like, if you were looking from the outside, okay, we'd say, hey, all right, here are those myofibrils reaching out like that from our end section. Well, if we zoomed even further in on that, because that's both actin and myosin, what we'd see is something that looks like this. Here we go. And remember, those Z lines are our actin. They're part of the actin molecules. And then inside of that, you got your myosin right here, the heavy chains with the cross bridges reaching out. So understanding that orientation just like that within the muscle fiber, how those kind of are related. Okay, next one. What specific protein within the muscle fiber was used by scientists to differentiate between fiber types? Okay, last week I posted that video of the skeletal muscle biopsy, and I talked about this a little bit. And what we were talking about here is our myosin heavy chains. So that's the specific protein within the muscle fiber. That is the first answer to that question. Okay, usually by scientists to differentiate between muscle fiber types. Remember, those kind of heavy chains, if we had to draw them like this, just like that, we have that intertwined nature. Here's the myosin heads, just like that. What we're doing is we have an antibody that binds specifically to that heavy chain. And those heavy chains are going to differ depending on the type of muscle fiber that they're in. Type 1, type 2A, or type 2X. The composition, the amino acids that make up those proteins in the myosin heavy chain are going to be different. Therefore, if you choose an antibody that only binds to amino acids that are in one of those but not the other, then that antibody can be bound to a dye and help you to identify what type of muscle fiber you are looking at. Okay, the main difference between those, the order of operations there with your the amino acids in those myosin heavy chains, is that they control how fast those myosin heads can detach from the actin. And think about that as far as a muscular contraction happening quickly or slowly. If those myosin heads take a long time to detach, well, that's going to slow down your overall muscle contraction. On the flip side, if those myosin heads can detach very quickly, then that's going to speed up your muscle contraction. That's what we're going to see in our type 2X, is those fast detachments. And that's what those difference between those myosin heavy chains are. Okay, letter C. List the muscle fiber types in order from most fatigue resistant to least fatigue resistant. How does this relate to their contraction velocity? Oh, we just did this. Here's type 1, most fatigue resistant. Then we move on to type 2A, moderate fatigue resistance, and then type 2X. Oops, let's go here. And our fatigue goes up as we go in that direction to the right overall. Okay, how does that relate to their contraction velocity? Well, if we put velocity right here as well, it would be along the same continuum. Velocity goes up as we move towards more fatigue prone, less fatigue resistant, and velocity goes down. Think about the skeletal muscle contractions of a marathon runner. Those are not very fast if you think about their like quad or their hamstrings compared to the muscular contraction of, let's say, a high jumper. The contractions that occur in that high jumper's quad when they are exploding off the ground to try and get over that pole are going to be a lot faster than a marathon runner who's doing that contraction, thousands of times over the course of the marathon. Okay. Last one here, letter D. Once an action potential has reached a muscle fiber, how is it propagated to reach the T-tubules? This is an important point because this gets to kind of a little bit of the minutia there, something that I'd really like to ask questions about on the exams. Once that action potential has reached a muscle fiber, how does it then get to that T-tubule? And the answer here is those voltage-gated sodium channels. If you remember back to our lecture on Thursday, we talked about the sliding filament theory and how once that action potential gets to the muscle fiber, we have our ligand-gated sodium channels right under that neuromuscular junction. However, that neuromuscular junction may not necessarily be right next to a T-tubule. So you need something to bridge that gap. You need to bring in sodium in an area that you don't have ligand-gated channels. Well, the benefit there is that you have those voltage-gated. So those voltage-gated are right next to the neuromuscular junction. So when that voltage changes in that NMJ, then it's going to be noticed by that initial voltage-gated. Once that first voltage gated goes, well then that's going to propagate and move that action potential down that muscle fiber to the T-tubule where it can eventually release that calcium. Okay, make sure to study those steps of the sliding filament theory. Very important for the exam tomorrow. All right, let's move on to some new stuff. Taking a quick step back, we're going to go back to the brain for a minute because I just wanted to review a couple different areas. It's important, we're talking about neuromuscular muscle contractions in this unit. So just understanding some of the different areas of the brain and what they control is going to be important as we move on and as you keep going with physiology in general. So let's start with the telencephalon. Might as well make this guy red to start. We don't have any other red areas. Here we go, telencephalon right there. Okay, and the telencephalon in general is going to be made up of the cerebral cortex. It's about 40% of our total brain mass. Most of the things that are controlled here are sensory and motor function. So if you're a soccer player, if you are, going up for a header, as you sense that ball making contact with your head, the ow that comes along with that is sensed in the cerebral cortex. The motor function, you moving your head towards that is also going to come from that cerebral cortex. Overall, we have 4 lobes of this. Not important for the depth of this class to understand what those 4 lobes are, but just understanding that there are 4 lobes associated with the telencephalon. Okay, next, diencephalon. My favorite. And hopefully you can see me outlining kind of that green section right here in the middle and coloring that in. Here is our diencephalon. And you're probably sitting at home right now being like, oh my gosh, I can't believe Dr. Johnson's such a nerd. He has a favorite area of the brain. Come on, nobody has that. Well, I do, and the reason is due to the subunits of this one. And there are 4 subunits, and you should know these. 4 subunits. And these are the thalamus, the hypothalamus, the epithalamus, and the subthalamus. I'll just put sub T in there for that. Okay, those are the 4 regions. And why do I like this one so much? Because it controls a lot of different stuff. Number 1, metabolic rate. Number 2, temperature. You have specific neurons in the diencephalon that are responsive to temperature. So when the blood transferring through that area of the brain increases or decreases in temperature, those neurons will either increase the rate of firing or decrease the rate of firing. Ever heard about shivering? That's where this is going to come from right here. Number 3, hormone secretion. It's not a subunit, but your pituitary gland is deeply connected to the diencephalon, specifically the hypothalamus. So a lot of our hormones come right from here. Number 4, blood pressure. We're going to go over this more when we get closer to the end of the semester. And last one, partial pressure of gas sensation. And the reason I put sensation in quotes there is because I'm sure that a lot of you have had changes in your partial pressure of gas in your blood. For example, if you did not grow up in Laramie and you moved here from somewhere else, with it being at higher altitude, the partial pressure of oxygen is lower. So when you first came here or when your relatives come to visit, guess what? That partial pressure of gas in their blood goes down. You don't necessarily sense that. You don't step off the plane in Laramie and go, oh man, that partial pressure in my blood is way lower right now. No. However, your brain does. And there are a lot of responses to that we're going to go over when we get to altitude a little bit further in the semester. So that's why it's my favorite area, because it controls so many really cool things. Now, we'll get to the cerebellum. We have 2 lobes here. Oh, this is our blue area right here in the back. This one. Oops. Maybe I can change the color and make it a little bit brighter. Here we go, cerebellum. Right back there. Cerebellum. 2 lobes. And this kind of is the pathway between different areas. So it monitors and coordinates the different areas. So this isn't necessarily, this is kind of like the air traffic controller seeing everything that's going on around and saying, okay, now it's safe for you to send that motor signal out to do that action that you want to do. Oh, wait, hold up, we got some breathing going on right now. Let's make sure we coordinate all these different situations. Also, it stores your movement patterns. So last week when we were talking about the theory of neural plasticity, that's where these motion patterns come from, your cerebellum. Okay, midbrain, pons, and medulla oblongata. All right, we kind of have 3 different areas right here. We have our little orange section right here. Let's go orange. And we can actually kind of circle it right there. Here's your midbrain. And if we want to talk about what that midbrain does, that's a very small little area. It's only 1.5 centimeters, but it deals with a lot of really important stuff. Vision, hearing, and alertness. Oh. So if you had a cup of coffee this morning, the neurons in your midbrain are what are activated, or there's some receptors actually there that are blocked due to that caffeine, and that will enable you to not, what it basically does is it stops the sleepy signals from coming from the midbrain. So it dulls those to make you feel a little bit more alert. Okay, pons, right below in that second kind of blue section, we can, let's do it in the blue, right here. So I'll put that circle around the pons. This is the neural bridge between the lobes of the cerebellum. So if we were looking at the brain from a different angle, if we kind of turned it away from us and we're looking directly at the back of the brain, there'd be 2 lobes of that cerebellum right at the back of your brain right there. The pons is what kind of connects those 2 with a little U-shaped right up like that. So even though we kind of look at it from the side and we can see it right there, think of this as kind of being that connection between the left and right side of the cerebellum. Okay, last one. What color do we have for this? Oh, purple. All right. Right down here is our medulla oblongata. All right. Another very important one, because this deals with ventilation regulation. Blood pressure, which kind of shares that a little bit with our diencephalon, and also your reflexes. So when you go to the doctor's office and they hit your knee and your leg goes up, guess what? That signal to extend your quad came from your medulla oblongata. And think about this geographically. Why does that make sense? Because a lot of these things we just labeled here below, we want to happen very quickly. We want our ability to respond to these situations to happen very quickly. we would not want our breathing to change very slowly in response to sensory information. We would want that change to happen very quickly. Okay? And if it's here in that medulla oblongata, we can have a shorter distance for those action potentials to travel before they get integrated and brought back out to the effector organs. So having them there in that medulla oblongata, what some people refer to as like your lizard brain, the area that's involuntary and you can't really think about, that's right there in the medulla. Okay, so quick little just anatomy refresher of the different areas of your brain, because the reason we bring this up right now, and you'll see this when we get to it a little bit later, in both our respiratory and our cardiovascular sections, having to do with the regulation of breathing and the regulation of your blood pressure. Okay, let's move on. Let's move back to the muscles. And we talked about that. We just started to get into the muscles last time, and we said, okay, we're talking about these different muscle types: fast twitch, slow twitch. Now I want to get into some of the sensory information coming from all of these types of muscles. Now we are talking regardless of the muscle fiber type, all these muscle fibers and tendons associated with them are going to have these organelles. Okay, the first one is our muscle spindle. So let's kind of zoom in here and let's look at this muscle spindle. The muscle spindle that we're talking about right here is of this total length. It's within the muscle fiber overall. Specifically, it is in one of your intrafusal muscle fibers. So it's on the inside. The extrafusal are out here. Here's an extrafusal muscle fiber. And if you were to break this down, what you would see in here, oh, look at this. You can see those little striations. Those are our Z lines. Okay, so those are the muscle fibers, the individual muscle cells, and those have actin and myosin in them that can contract and shorten. Well, they can also, what's happening here, is lengthen. What happens when that muscle spindle lengthens? This area right here has a sensory fiber around it. You can see the sensory fiber wrapped around that muscle spindle. And guess what? This is going to send some information to your brain. When this muscle stretches, you can see it lengthens. The sensory fiber is going to sense that lengthening and respond. So what's going to happen here? And what we're showing down here is unstretched muscles. We have just this regular action potentials generated at a constant rate. However, after that stretching, we're going to have an increased rate of action potentials. Something is changing. We need to do something. All right? So if we go back to our muscle spindle, what happens? We know, let's just do some definitions first that we talked about. This is within the muscle fiber. And I know you're thinking kind of, yeah, duh, right here. But when we get onto our Golgi tendon organs, those are not necessarily going to be in the muscle fiber. So we want to make sure we list out all the things that are different about the muscle spindle. Now they respond to stretch with increase action potential firing rate. Now what happens? When they increase their firing rate, that signal then goes to the brain. What is the response to that increased firing rate? If you're just sending more signals, it doesn't really matter too much. But if we respond with the stretch reflex, now, everybody either consciously or unconsciously knows about the stretch reflex. If you've ever done a vertical jump test or tried to jump really high, you know what that looks like. You would not go to jump really high. This is what I do when I want to dunk a basketball. Okay, I do not just go stand under the hoop and just flat-footed just jump up as high as I can. No, what I do first is I do that counter movement where I move down and then I propel myself up to dunk the basketball. I can do that. If you want to see me do that, just bring a basketball to my office. I'll walk right down to Corbett and I'll dunk a basketball for you. the stretch reflex you might also see with push-ups. If anybody's ever done a hand release push-up where you go down to the ground, take your hands off of the ground, and then put them back on the ground and do a push-up, that is much harder than coming down, turning around real quick, and going up. Even if you go to the same depth, even if you touch your chest on the ground in both versions of the push-up, it's way harder to do that hand release. Now the question is then, why? When I take my hands away, what happens is I reduce the stretch on my pec muscle. If I reduce my stretch, I turn off the stretch reflex. So the only thing that can happen then is I have to actually just produce force due to voluntary skeletal muscle contraction. If I allow myself to do that rebound right at the bottom without taking my hands off the floor, well, guess what? I get a reflex that kind of helps me along with some of that push. Okay? So what happens here is step number 1 in the stretch reflex, muscle is stretched. And we already talked about what happens when the muscle's stretched in these muscle spindles. Well, we get an action potential increase. That action potential, the afferent nerve fiber sends sensory information to the CNS. The result will be a contraction in the stretched muscle. Contraction in the stretched muscle. So our push-up example we were talking, as you're going down, your pec muscle is stretching, 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 stretching. When you get to the bottom, you get a lot of stretch, okay? And your body says, whoa, that's a lot of stretch. I better contract that to protect that muscle. So as you're turning around, that amortization phase at the bottom of your push-up, where you're changing direction from eccentric contraction as you're slowly lowering yourself down, to concentric contraction, okay? Muscle is stretching, muscle is contracting. Muscle stretching, or muscles getting longer, muscles getting shorter. That's flip between those two different kind of angles is going to be driven by your muscle spindles and this reaction right here. Okay, so that handles 1, muscle spindle. Let's move on. Let's go to our Golgi tendon organ. Here's a great infographic that I found. And this is talking about the interaction between your quads and your hamstrings. And if we had to talk about both of these muscles, one is going to be our antagonist and one is going to be our agonist. All right? The agonist muscle in this situation right here is going to be the one that is being stretched. The antagonist muscle is going to be the opposite muscle. If you think about, any English classes where you had to deal with antagonists, that's a person who's going to be the opposite of what you want to do. Okay, so the first thing we need to know about these, let's go back over here and let's just write this down. Well, it's a Golgi tendon organ, so it's in the tendon that's at the muscle joint. So generally, this exists to protect some of our joints. Aha! Because we don't want too much stress at these joints. We don't want too much stretch at these joints as well. So in this example right here, 1, the quadriceps strongly contracts, the Golgi tendon organs are activated. All right? When that quad contracts very strongly, all right, what's going to happen is it's going to put some stretch on that patellar tendon right there where the Golgi tendon organ is. 2, the afferent fibers are going to synapse with interneurons in the spinal cord. Okay, remember this is a reflex arc right here. So this isn't going up to your brain. It's turning around right at your spinal cord. Now, two signals go back. If you zoom in really close right here, what you can see here is a negative sign on that red efferent neuron going back this way. Let's make that red efferent neuron. There's a negative signal going back here. But if we look over on the other side, we see here there's a positive sign on the efferent neuron going to our hamstring. Okay, so we have a lot of stretch that's caused by a muscular contraction in our quad. Our quad is contracting very, very quickly, okay? And what's going to happen now is that puts some stretch. So what might happen here is you might have like a rock sitting right here in front of that person's shin. And now they're going to contract as hard as they can, but guess what? That muscle can't shorten. So it's going to create a lot of stress. What's going to happen then is the body's going to say, hey, we're creating a lot of force, putting a lot of stretch on that tendon. We have to protect that joint. We want to make sure that that doesn't happen. So we then send a negative signal to our quad and a positive signal to the hamstring. So it's going to relax the quad and it's going to contract the hamstring and move that leg in the opposite direction, away from the stress. Okay. So I wonder if anybody watching this has ever done something, if you've been on a sports team or anything, or maybe done some yoga, you may have done something called PNF stretching, neural facilitation stretching. This is when you'll go into a stretch and then the person will have you contract the muscle that you're stretching and then relax, and then, oh, after that I can stretch a little bit further. Well, guess what? That's because you're using the Golgi tendon organ stretch response to get that. Okay, so it protects the muscle and tendon from injury. And when a stretch is sensed, you're going to get one, inhibition of the agonist muscle. So whatever muscle is being stretched, that one's going to get inhibited. Two, you're going to get activation of the antagonist. In this case, it's the hamstring, so the hamstring is going to then contract. So you're going to react to a contraction-mediated stretch. So this isn't necessarily a passive stretch. This is a stretch that's caused by you contracting a muscle. For example, that we gave before was you're pressing that leg up against a rock that's not going anywhere. That is still going to cause a stretch. Last one, Pacinian corpuscle. This one is pretty intricate overall, but also in your tendon, let's keep that little note over here. You have these little nerve endings right here that sit inside these layers of myelin. Now, we've seen myelin before when we're talking about nerve transmission signals. Well, what this does is it protects that nerve ending because it insulates it. Okay, so that does two things. It stops it from being just casually activated by other action potentials moving through that area. But it also creates this capsule around it, the Pacinian corpuscle, that kind of senses or acts as a pressure sensor. All right, it's going to be able to sense when it gets depressed. So when something comes in and puts a lot of pressure on that Pacinian corpuscle, look what happens. Well, those ion channels are going to open up inside when it is stretched. Aha! So when that pressure comes, it's going to actually stretch right down here in that nerve ending and allow those sodium channels to open. Once those sodium channels open, we can then create an action potential. That action potential is going to result in a contraction. Okay, so we're very similar to the original muscle spindle stretch reflex, but this one's a little bit different because there's no stretch reflex specifically to the muscle. This is in the tendon, and it has to do with pressure. Aha, responds to quick and deep pressure. And the result is a contraction. And the example I always give for this one is remembering back in my high school days when you're sitting there, maybe you're going to a sports event or something like that, and you're sitting next to your buddy, and your buddy reaches over and goes boom right on your quad and gives you a dead leg. What happens when that happens? Well, your quad contracts and you're going to feel that deep pressure. That's why you have a contraction in relationship to that due to the Pacinian corpuscles. Okay, so those are our three big skeletal muscle organelles that are a part of this unit right here. Let's take a quick deep breath right now because we're changing topics once again. We talked about areas in the brain. We talked about how skeletal muscle can sense different stretches and respond to those. Now we're moving into anaerobic energy, okay? So if we want to do some work, where does that ability to work come from? And what I'm going to do now in this space right here, I'm going to draw my favorite figure in exercise physiology. We'll draw our y-axis. We will draw our x-axis, and on our y-axis we're going to label this as percent of max energy production. And right up here we have 100%, and down here we have 0%. And then on our y-axis we're going to put time. And we're not really going to go to scale on this one, but I just want to put a couple landmarks in here. Our first one is at 2 seconds. Okay? Our next one is going to be at 10 seconds. Then we're going to go a little bit further, and we're going to go to 2 minutes. And then we're going to break our axis. Okay, and then out here we'll go to 2 hours. I put that little mark in there. If you ever see that in one of your figures, basically what that means is we are changing the scale of our axis, because this distance right here is about the same as this distance right here, but in the first one we only went from 10 seconds to 2 minutes, and in the second one of about the same horizontal space we went from 2 minutes to 2 hours. So we put that little break in there in the axis to alert the reader to say, whoa, we're changing our units here, or the scale of our axis. So just be alert that this horizontal distance is not representative of how far we've gone. Okay? A little about making tables and figures. So what we're going to do here is talk about our ability to do work. We know this needs to come from adenosine triphosphate. And the first ability comes from our stored ATP. So right now, all of us sitting here have a certain amount of ATP in all of our skeletal muscles ready to go to work, ready to do something. So we'll start right from here, and we'll go all the way up to 100%, but down very quickly, and then just sitting right above that 0% for the rest of our time here. Okay? So right now, you have some stored ATP in your muscles that are going to help with your ability to have muscle contractions. The next thing we're going to talk about is the ATP PCR system. I'm sure some people in this class have taken creatine before. Do you know why you took creatine besides getting jacked so you can go on spring break? No. Well, the main reason is because creatine is part of this guy right here. If you consume more creatine in your diet, you can increase the phosphocreatine in your skeletal muscle. If you increase the amount of phosphocreatine in your skeletal muscle, you can help regenerate more ATP. Okay? So phosphocreatine can add on a phosphate to ADP. ADP, adenosine diphosphate, plus the phosphate from creatine can make ATP. Okay? So as you are doing your skeletal muscle contractions in those first 2 seconds, you're making a lot of ADP because that stored ATP is being broken down. Well, as that's happening, your phosphocreatine kicks into gear and says, whoa, we got a lot of ADP here. Let me regenerate this as quickly as I can. And so we have our ADP, which will last for about 10 seconds and then kind of hover here at a very low amount as you continue your exercise. The reason that creatine is normally taken with resistance training programs is, think about it. Most of our resistance training, if you get on the bench and do a set of bench press, you're probably going to be on there doing work for about 10 seconds. If you have more adenosine triphosphate being regenerated, you can either continue doing reps for a little bit longer, or you might be able to lift a little bit higher weight for those 10 seconds. Because you're kicking in. If you supplement, this will go like that. Aha. Next. We're going to move on to our next color right here. I usually do purple for this guy. And this is going to be kind of glycolysis. And we're going to talk about that at the very end of today's lecture. Where does glycolysis fit in? This is aerobic, or anaerobic, sorry. Meaning we do not need oxygen. This one is going to go right like this. And it's going to maintain itself a little bit higher. But what we see here is we have about a limit of about 2 minutes. Now, if anybody's ever run track before, there's the event which I consider to be the most painful event in track, and that is the 800-meter run, 2 laps around the track. That duration of about 2 minutes of work, for me, probably closer to 2.5, 3 minutes. But if you're very, very fit, that time is about 2 minutes to do half a mile around the track, 800 meters. Okay? And the reason that's so painful is because you're pushing past your stored ATP. You know, as you're going around that first curve, you're like, this is totally easy. Everything's cool. And then you get to about that 10-second time point once you get off that first turn, when your stored ATP is gone, your ATP PC system is gone. Now you're kicking into glycolysis. But as you're getting towards the end of that second lap, you're running out of the ability to perform glycolysis. So all you're going to sense then is a lot of skeletal muscle discomfort due to high lactic acid concentrations and change in your internal pH. Okay? So here's the metabolic reason why running an 800 or doing something about as hard as you can for 2 minutes is really, really hard. Okay? The last one we're going to add in here, we'll do it in brown. Very, very low. And this is going to be your aerobic metabolism. So that's probably your electron transport chain, your Krebs cycle. You're going to be metabolizing fat, carbohydrates to produce a lot of ATPs through this system. What we're generally going to deal with in this section right here is these first three. We're going to move on to our aerobic metabolism in our second unit. But in our first unit, we're talking about anaerobic. And to talk about anaerobic, we have to talk about each of these individual systems. So what we want to figure out first is how much work we can do with our stored ATP. All right? It's important to do the math to figure out why does our ATP only last 2 seconds. All right? So we have some conversions that we know about here with how much work. The first one is that 1 kilogram of muscle can store about 3 to 8 millimoles of ATP. And then the other thing that we need to know is that 1 mole of ATP is equal to 7.3 kcals. All right, so with this, we can then determine if we knew a person's skeletal muscle kind of weight, we would then be able to determine how much work they can do, because we have a measurement of energy here, calories. Right? So let's do an example with me. For example, let's say I have 30 kilograms of muscle in 1 Dr. J. Okay, these are our units. Kilograms of muscle on the top and Dr. J is on the bottom. So we have 30 kilograms per Dr. J. Now, let's just multiply by 1. We can multiply by 1. We know that if we're at 3 millimoles, if we take the low end of this example right here, we have for every 3 millimoles, we know that's equal to about 1 kilogram of muscle. Okay, well then we need to multiply that out because we know that there are 1,000 millimoles of ATP in 1 mole of ATP. And then the last one we'll do is we know that there are 7.3 kcal in 1 mole of ATP. Aha! So now we can go through and we can get rid of our units. So we know that we're getting rid of kilograms of muscle, we're getting rid of millimoles, we're getting rid of moles, and what we have here is overall, this is going to equal about 0.657 kcals per Dr. J. So within me right now, I have about 0.657 kilocalories of stored energy. Now, think about the last time you went to Half Acre before the pandemic, when you could actually go to a gym and you got on the treadmill and looked at that calorie burn because you wanted to make sure you were getting ready for spring break at the time, you're trying to get that summer bod, so you wanted to burn some calories, right? So think about how long it took to get 0.657 kcals. Was that a short duration of time or was it a long duration of time? Think about it. I've gotten on that treadmill before, or the stair stepper, and burnt 500 calories in a workout. I'm cranking on that bad boy. So this is only 0.657. So overall, that's a very short amount of time. So for example, 0.657 kcals equals 1 minute of slow walking, 20 seconds of marathon running, or 5 seconds of sprinting. And we gave our general example up here of about 2 seconds for this, but you could probably stretch it for about 6 seconds. So what that tells us is that we don't have very much ATP stored in our body. However, what we do have, the benefit of this, is it gives us that ability to produce a large amount of force for a very short duration immediately. There is no hesitation in the ability to use this ATP. And so this is, if you have that immediate threat come at you, you can run away very, very quickly, right? That you don't have to sit there and warm up and do a bunch of stretches before you run away from a bear, right? You can get up from your chair immediately and run away. Now, that will last for about 5 seconds. And after that, what is next after our stored ATP is used up? That's when our ATP PC system comes into play. Okay. So what's next? Well, this is our phosphocreatine. Let's move this guy up right here. And we're going to label this as PCR. What's going to happen with that is that phosphocreatine can then dissociate into creatine, and a phosphate unit. In parallel with that, we have ADP. ADP can interact in parallel, just like this, and pick up that phosphate. If we pick those two up together, guess what we get? ATP. Fantastic. So like we said before, if you supplement with creatine, or even if you don't, you have phosphocreatine in your bloodstream and in your skeletal muscles right now. As your stored ATP gets used up, you create more ADP. As that ADP concentration starts to go up, your body tries to supplement that and regenerate that very, very quickly by taking a phosphate off of phosphocreatine, adding it to ADP to make ATP. This enables continued MC, muscle contraction, without oxygen. Fantastic. So we can continue to do anaerobic metabolism. We can keep contracting our muscle without having to breathe. If you got down on the bench press and held your breath and repped out 10 times, it probably wouldn't be very comfortable. However, you'd be able to do it. A lot of sprinters can run that 100 meters, okay, which takes them about 10 seconds, takes me about 20, without breathing too much. They breathe a lot afterwards, but not so much during, because they have their phosphocreatine system. So, what happens then after? You've done your 10 sets or your 10 reps on the bench press. You've used your phosphocreatine to enable yourself to keep doing muscle contractions while you're doing that bench press exercise. Well, afterwards, we're going to take that creatine and we have to make it back into phosphocreatine. Well, if we have that phosphocreatine with that phosphate group on there, we need to add a phosphate to the creatine in order to get there. Well, where the heck do you think we get that? ATP. So now we are resting. We don't need that adenosine triphosphate in order to perform skeletal muscle contractions, so our ATP concentration in the skeletal muscle is going to be a little bit higher. What we're going to do is we're going to use that ATP to regenerate, give that free phosphate onto here, and we'll move off and create our ADP. Right, like that. And let's make this the same color to make that a little bit more obvious. Okay. So about 60% of your creatine in your body is phosphorylated at rest. Let's put that little note here on our side. So what that means is if you consume more creatine through supplementation or through other dietary methods, well, 60% of that is going to be phosphorylated. So if you consume more and your overall creatine pool is higher, well, guess what? Your overall phosphorylated creatine is going to go up as well. So that's why supplementation works, because you have more of this right here to enable the continuation of muscle contractions without oxygen. So this comes from our ADP at the bottom left. This comes from stored ATP. Goes right like that. And what we would say overall is that if we wanted to talk about when these two things were occurring, we're using our ATP to regenerate phosphocreatine at rest. And we're using our phosphocreatine to enable skeletal muscle contractions during exercise. The last thing we need to know about is in the middle of this, we'll do this color. Make it, we have an enzyme that's going to help. Creatine kinase is the enzyme that enables this reaction to move in both directions. Without this enzyme, you would not be able to add on that phosphate or take off that phosphate. When we look for markers of skeletal muscle damage, we measure creatine kinase in the blood because this enzyme is supposed to be in the skeletal muscle. If that skeletal muscle breaks due to skeletal muscle damage, we will find more creatine kinase in the bloodstream. Aha, because that's that enzyme that performs this high intensity exercise, right? Okay, so after our stored ATP is used, our phosphocreatine comes in and enables us to keep on doing those high intensity skeletal muscle contractions without oxygen for about 10 seconds. And then when we are at rest, that creatine gets regenerated back into phosphocreatine through the use of ATP. So what happens? What's the last resort? Overall, our ATP PCR system is all used up. Now we want to continue to make some we want to be able to continue to have skeletal muscle contractions still without using oxygen. What's our last resort? Well, let's take our muscle. Here's our skeletal muscle belly, just we talked about the other day. And inside that, if we have glucose, and we're going to go over this at the end of today's lecture, we can use glycolysis to create pyruvate. And we take that pyruvate, if we zoom in here, and we say there is no O2, well, then we're going to make our lactic acid. All right, we're in the skeletal muscle there. Let's draw one more thing. We'll say off that glucose, we're going to make some ATP. Fantastic, but we have this lactic acid. We're running out of our ability to do this. We made our lactic acid because there's no oxygen. There's not any oxygen accepting electrons at the end of the electron transport chain. We don't have the ability to convert our pyruvate into our acetyl-CoA. So what we're going to do here is we are going to bring that lactic acid somewhere else. Let's draw a single blood vessel attached to that skeletal muscle, and it's going to go over to our liver. And then on the other side of that, we have a blood vessel going back in the other direction as well. Once that lactic acid gets into the bloodstream, it's going to dissociate into lactate and our hydrogen ion right there. And so you might say, okay, well, why does your blood pH change when you exercise? Well, it's because that hydrogen ion is going to dissociate off of lactic acid and then drive that pH down, right? Well, that lactate itself can keep moving on and go to the liver. Once that lactate gets inside of the liver, it can undergo gluconeogenesis, where it's going to create pyruvate, and then create glucose, which then can get transported back to the skeletal muscle. Overall, this process right here is known as the Cori cycle. So now we've covered kind of the three main ways that we can produce energy in the very early stages of exercise. We have our ability to use our stored ATP. We have our ability to use phosphocreatine to then supplement and create some more ATP. And as a last resort, when we're using up all of that ATP, we can break down some glucose, make some lactic acid, and get that over to the liver to help regenerate that glucose and hopefully supplement our glycolysis. All right, we're going to get to glycolysis, like I said, at the end of this lecture, but this is just one way that we can help regenerate that ATP without oxygen. Okay, we're going to take a little break here. This will be part 1 of today's lecture. I'm going to post 2 more parts, so today's will be a 3-parter lecture that will hopefully enable you guys to watch these videos a little bit more easily.